Lower limb prosthetics can place a significant financial burden on patients and their families. Current prosthetics are able to meet patient requirements for functionality, durability, and aesthetics. However, there are not any commercially viable low-cost options. Because of this, there is a huge unmet clinical need for a low-cost device that can restore normal gait and limb alignment for transtibial amputees.
The most common reason why a person would need to have their leg amputated is because of the poor circulation of diabetic and arterial disease patients that develop ulcers on their feet. 73,000 lower limb amputations occur every year, which leads to patients losing their normal walking ability and alignment. 55% of the diabetic amputees even require amputation of their other leg within 2 to 3 years. The current solution is an expensive prosthetic leg that can cost up to $50,000. So here are some realistic constraints for this device. There's economic cost and risk involved with developing and distributing a new product on the market. There are also environmental constraints, such as adverse weather and terrain, that could compromise the appearance or functionality of the device. Sustainability constraints involve the supply of this device not efficiently correlating the demand from the consumers, and the manufacturing process could be lengthy. New sores on the residual limb can develop if the alignment is subpar, and if the device detaches, that also arises a safety concern. Finally, there is a social constraint if the user does not feel psychologically comfortable with a prosthetic leg that doesn't look as real as possible.
After considering all factors and speaking with our Hanger Incorporated sponsors, we have come up with a list of design requirements for our finished product. As you can see, they are organized from high to low priority level, with high priority requirements being a must-have, while the medium and low priority requirements are more for if time allows. The most important requirement is to increase the level of alignment from last year's senior design project. The quantitative criteria that we have assigned to this requirement is to be within 1 degree of the bench alignment. Next, as Sarah previously mentioned, we want our device to total cost of less than $5,000. We also need our prosthetic to be durable, which includes making it safe within 3 to 5 times the safety factor. Our goal is for the product to be able to withstand 4 years of normal wear and tear without hindering the patient's walking or their quality of life. Finally, one of the main medium-level requirements that I want to touch on is ease of attachment. Tripp will talk a little bit more about it next, but quantitatively, we want the patient to be able to put on the prosthetic in under 3 minutes.
The finished device will be low cost to both the patient and their insurance provider, exoskeletal for ease of manufacturing, and meet or exceed current industry standards for functionality, durability, and aesthetics. When combined, these 3 features will allow our device to become a disruptive market solution.
As stated earlier, the most important factors when brainstorming a design were alignment capabilities and cost. We chose to focus on attachment methods with the monolithic prosthetic, as we felt this would allow us to have greater control over the alignment capabilities. The 4 methods of attachment we came up with were suction, sleeve, lock and pin, and Velcro. Using the Pew matrix and the priority of the different comparison categories, the suction method was shown to be the most effective for our design requirements. An image of this type of socket is shown in the bottom right image. For our deliverables over the next year, we will be developing a design and prototype of the socket and its attachment. Once our prototype has been tested and shown to perform up to our standards through the mechanical testing and finite element analysis, we will perform gait analysis testing on the prosthetic, given the opportunity to work with the patient to test our alignment properties. In total, we will be handing over mechanical testing results, bill of materials, socket design and attachment with the fabrication and manufacturing instructions, and gait analysis results. All of this will be in accordance with ISO standards through a DHF file submission.
Stakeholders for this project include Hanger Incorporated, Texas A&M University, and our own senior design team. Hanger is the prosthetic company that is sponsoring this project both financially and professionally. They will be engaged with communication, guidance, and consultations throughout the different stages of this project. The team will obtain valuable feedback and resources from them in order to complete a successful prototype. Texas A&M will provide us with the resources that are needed to conduct software analysis and mechanical testing. We will receive feedback from the senior design professor to improve the design history file as well as our presentation abilities. Finally, we will work collaboratively as a team to provide internal feedback and conflict resolution as we complete the stages of this project as efficiently as possible.
Over the course of the next 2 semesters, we will first work to integrate a socket with the existing prototype. This prototype was developed by last year's senior design team. Once we have done so, we will perform finite element analysis on our prototype system. On the right, you can see an example of some results of a very basic FEA performed on last year's prototype. What this shows is the anticipated forces that would be distributed throughout the prosthetic during the heel strike phase of the gait cycle. As you can see, this image has different colors which correspond to the different magnitudes of forces. When we perform our FEA on the combined prosthetic and socket, we intend to analyze the soft tissue rigid body system, which is comprised of the residual limb, the prosthetic itself, and the ground. FEA is done entirely on a computer, which means this will allow us to rapidly iterate our prototype, making alterations as needed to increase limb alignment or decrease pressure points or stress concentrators within the prosthetic. Once this has been completed, we will move on to developing and implementing a mechanical testing protocol. This will be done to ensure that the device is suitable for use. Some things we will analyze with this will be the safety of the device under different loading conditions, as well as the durability or wear resistance of the material we create the device from.
In order to ensure that we are creating the best device possible, we need to take into consideration the competitive alternatives and methods that have previously been tried. As you can see in the table, there are some risks associated with these alternatives. Specifically, the Echelon foot and the Autobach exoskeleton prosthetic have been shown to have limitations on factors such as weight limit and ease of changing parts. Overall, these 2 models are more complicated than the kind of prosthetic that we are trying to achieve. The monolimb option is simpler, but it also reduces the patient's range of motion. As stated previously, we do not want our device to inhibit the person's walking, but rather we would like for it to allow them to maintain their quality of life. Finally, the carbon fiber composite option ended up failing its mechanical testing. This information is significant to us, both for deciding on what material to use and for ensuring that we perform more than enough mechanical testing. The goal is for our prosthetic to be suitable for everyone, even for patients who may weigh more or who may have a more active lifestyle.
In closing, we would like to reiterate that we will be focusing on the analysis of the existing prototype and continuing the work done from the previous year. We would like to thank Hanger and the representatives for their help in the understanding of this project and the importance any significant findings would have on the prosthetic industry. Prosthetic limbs, oh, damn it, I don't have anything else. I don't think that was 20 seconds.
No, that was only 10.
Right. In closing, we would like to reiterate that we will be focusing on analysis of the existing prototype and continuing the work done from the previous year. We would like to thank Hanger and their representatives for their help in the understanding of this project and the importance any significant findings would have on the prosthetic industry. We would also like to thank them for giving us this opportunity to work with them on an important project such as this one.